Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. And we have so much science. Later in this episode, we're going to bring you a roundup of all things Perseverance rover and an interview with Dr. Elizabeth Newton about the TESS mission's hunt for young maturing planets. Before we do that, however, we're going to do a rapid fire rundown of the news.
And we're going to start with the nearby black hole Cygnus X1. Detected as a powerful source of X-rays in 1964, this compact object that is located in a binary star system was the first object assumed to be a black hole. And until a new paper in Science, we thought it was pretty average, with a 20-ish solar mass black hole orbiting next to a large blue giant. The problem is we may have mismeasured just how far away this system is. Research led by James Miller Jones now shows that Cygnus X1 is roughly twice as far away as we thought and needs to be a whole lot bigger. Basically, we found out that the nearby big monster is actually farther away and a much bigger monster, and we're no longer sure how it formed. Black holes from single stars aren't supposed to get this big. That said, according to my doctor, I'm also not supposed to get this big. Let's face it, sometimes mass finds a way, and neither I nor the universe like to stay within the limits placed by science.
Black holes come in all sizes and form in a lot of different ways. A single star collapses, one object eats another. Smaller black holes merge into bigger black holes. Turbulence collapses a lot of stuff in the early universe into supermassive black holes. There's a lot of ways to make black holes, however you make them. Once you have that black hole, you have a massive gravitational potential that, just like a bike cruising down a mountain can get accelerated to high velocities, particles getting near that black hole can get accelerated to massive energies. Occasionally, we find small particles called neutrinos with massive energies, and according to a new paper in the Astrophysical Journal with lead author A.V. Plavin, these neutrinos probably get generated in the environment of supermassive black holes. These results come from looking at the sources of a bunch of high-energy neutrinos, 200 tera electron volts and higher, and saying that they consistently appear to consistently come from the direction of a special kind of active galaxy called a blazar.
But again, the universe doesn't like to stay within limits. Plavin and company promoted their results on February 22nd. The exact same day, a different paper came out in Nature Astronomy documenting the story of a 200 tera electron volt neutrino that did not come from a blazar. Nope. It appeared to have come from the destruction of a star by a black hole in the outskirts of a distant galaxy. In this case, the neutrino was detected as well as the bright flash of light of the star being consumed. Second author Sjort van Veltzen admits the origin of cosmic high energy neutrinos is unknown, primarily because they are notoriously hard to pin down. This result would be only the second time high energy neutrinos have been traced back to their source. So, yeah, in theory, high energy neutrinos should come from active galaxies, but occasionally reality is going to throw us a neutrino from a shredded star well, because it can.
Theorists live a hard life. They try and figure out what should be happening, while observational folks are out there looking at what is actually happening. When the theorists get it right, they can get a Nobel Prize. But when they get it wrong, it's a bad day that nobody else remembers. Enter theorists Louise Alexandra Coston and Martin Segret, who on February 17th published an article in Science Advances describing how subglacial lakes in the Antarctic could support life. They are cautious, stressing microbial life could exist, and explain that, here I quote, as they have no access to sunlight, microbes in these environments do not gain energy through photosynthesis, but by processing chemicals.
That February 17th paper, well, it was in the works for months, and just 2 days before it came out, a group of scientists announced how they had quite accidentally discovered not just microbial life, but sea sponges and other weird critters, happily proclaiming why, yes, we can exist beneath the Antarctic ice shelf. This isolated water between the seafloor and the glacier isn't exactly a subglacial lake, but this wasn't someplace anyone expected to find life. These critters were found living on a boulder 260 kilometers from the ice front, while the researchers were digging boreholes for other geological and glaciological studies. This was a normally completely dark place, and the nearest sunlight was somewhere between 625 kilometers and 1,500 kilometers away. Clearly, theorists need to dare to dream their life forms bigger, because life will find a way.
With so many missions going to Mars, the question on many minds has become, can life find a way on Mars? New experiments performed by NASA and the German Aerospace Center find that Earth life will unhappily survive, at least temporarily, in Martian conditions. Joint first author Marta Filpa Cortasa explains, we successfully tested a new way of exposing bacteria and fungi to Mars-like conditions by using a scientific balloon to fly our experimental equipment up to Earth's stratosphere. Some microbes, in particular spores from the black mold fungus, were able to survive the trip, even when exposed to very high ultraviolet radiation. This is further evidence that black mold refuses to die. And this research gives us further reason to keep sterilizing all the spacecraft we send to Mars. If Mars has native microbes, we really don't want to kill them with our microbes. Or accidentally generate a super microbe by letting things crossbreed. Mars does not need a black mold problem.
In parallel with that high altitude work, a team at the University of Vienna was looking at the chemistry of Mars to see if it could support life. Specifically, astrobiologist Tetiana Miljovic ground up a tiny piece of a Mars meteor and built a tiny Martian environment to see if a kind of microorganism that eats rocks, a chemolithotrope, would eat Mars rocks. The microbe, scientifically named Metallosphaera sedula, did indeed live. According to Miljovic, grown on Martian crustal material, the microbe formed a robust mineral capsule comprised of complex iron, manganese, and aluminum phosphates. Apart from the massive encrustation of the cell surface, we have observed intracellular formation of crystalline deposits of a very complex nature, which we did not observe previously when cultivating this microbe on terrestrial mineral sources. Yep, yet again, life found a way, because it always does.
The Mars Perseverance rover is on a mission to find fossil life and to collect samples to someday be brought back to Earth. And you gotta wonder if there will be life in those samples. But more on that after this break.
I thought about being all snarky about our next story, but I can't find it in me. I'm too excited. At approximately 20:55 UTC on February 18th, Percy landed on Mars. I admit that I might not have been as hyped up as possible at the time of the landing because I was too busy being the consummate professional that I am, and was a bit busy interviewing guests and keeping a show running. But that doesn't mean it wasn't amazing. We have, once again, landed a small SUV on Mars. Perseverance is the last of 3 missions launched last July to arrive at the Red Planet alongside the United Arab Emirates Al Amal and China's Tianwen-1. Unlike those other 2 missions, Percy didn't settle into a Martian orbit first. Nope. The US mission screamed in toward the surface immediately and went right for the landing, using the same method as Curiosity, sky crane and all. There are a lot of differences between the previous rover and Percy, though. First, Perseverance is explicitly going to look for signs of ancient microbial life. While previous missions have happily made progress toward determining if life was possible on Mars, This is the first mission that has the instruments to actually seek out those new life forms. Maybe new life forms? We won't know unless we find them. Additionally, Percy carries a microphone, a first for a Martian rover, and an instrument requested for decades. In fact, we have an 18-second clip of sound from Mars. Take a moment to appreciate the scope of this clip. We have recorded sounds from another planet. Credit where credit is due, though. The Soviet Union did this first with the two of the Venera missions, 13 and 14. Let's take a quick listen. And of course, it wouldn't be a Mars mission these days without images from the High Resolution Imaging Science Experiment, or HiRISE, aboard the Mars Reconnaissance Orbiter. Not only did HiRISE capture all of the various bits of the descent system on the surface, but there is also an amazing image of the rover descending on its parachute. This is a particularly amazing image, as HiRISE isn't a camera in the point and shoot respect. It's a push broom scanner, which means it's like using a fax machine to capture a photo of an airplane that's in flight. NASA wrote the extreme distance and high speeds of the two spacecraft were challenging conditions that required precise timing, and for the Mars Reconnaissance Orbiter to both pitch upward and roll hard to the left so that Perseverance was viewable by HiRISE at just the right moment. We also have video. The video covers the landing from the parachute deployment all the way to touchdown, and we'll show you a couple pieces of the footage. The first is the parachute opening, more on that in a moment, and the heat shield separation.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Here. Applicate indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity.
And the second clip begins when the rover turns on its thrusters and the sky crane begins to deploy.
Started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
I get teary-eyed every time I watch it. Simply stunning. That is Mars, everyone. Mars. Whew. But it's not just about the landing. Mastcam Z is a pair of zoomable science cameras, and they've already captured their first calibration images. Plus, there's SuperCam, which has a pulsed laser to study rock and sediment chemistry and contains that microphone we mentioned earlier. There are two instruments, the Planetary Instrument for X-ray Lithochemistry, PIXL, and the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, SHERLOC, to do close-up geology. SHERLOC even has an imager called the Wide Angle Topographic Sensor for Operations and Engineering, or WATSON, that will be used to map out minerals and organic molecules on the surface of rocks. There's also the ground penetrating radar called the Radar Imager for Mars's Subsurface Experiment, RIMFAX, the Mars Environmental Dynamics Analyzer instrument to study climate and dust, the Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, to try and manufacture oxygen out of literally thin air. And last but not least, the Ingenuity Mars helicopter. Ingenuity is an engineering demonstration attempting to perform controlled flight on another world. Ginny has already reported that everything is nominal, and now we wait for a month or two before operations are attempted. Overall, Thursday was an amazing day. Percy is safe on Mars, and now we can finally talk about all the great science that will come out of this mission. Oh, and about that parachute, do yourself a favor and search for Perseverance parachute code. You might find you want to dare mighty things. After the break, we'll be back with a new story of exoplanet discovery and an interview with the lead author. Welcome back. Our last story has two basic parts. One part is the discovery of a trio of exoplanets orbiting a relatively young star called TOI 451. The other part is that the star system resides in a stellar stream, which is pretty neat if you ask me. Let's quickly talk about that stellar stream. These streams happen when galaxies collide with other galaxies or with star clusters, and the smaller object gets pulled apart by the gravity of the larger object. The process is sort of like how meteor showers happen, but instead of debris from a comet, you have debris from a galaxy stretching out in the original orbit. This particular stream is called the Pisces Aerodynamic stream due to its location in the sky, although it stretches across 14 different constellations. The stream is likely from when the Milky Way collided with a star cluster or dwarf galaxy and is about 1,300 years long. Discovered in 2019, the Pisces Aerodynamic stream was found in Gaia data, and then test data was further analyzed to find the age of the stars in the stream. These stars are about 120 million years old, similar to the Pleiades cluster. This also makes them 8 times younger than the previous estimate and a fantastic observational laboratory for studying planetary formation and evolution. Now, onto that system that was discovered around TOI 451. The star is about 400 light years away, has about 90% of our own sun's mass, is 12% smaller, a little cooler, and gives off about 35% less energy. It rotates every 5.1 days though, and that makes the rotational speed 5 times faster than the sun. In the system itself are 3 hot worlds. TOI 451b is closest to the star, about twice the size of Earth, and orbits in less than 2 days. TOI 451c is next closest, 3 times the size of Earth with an orbit of 9.2 days. And TOI 451d is 4 times the size of Earth with a 16-day orbit. Since the system is relatively young and relatively close, astronomically speaking, scientists are excited to study the planets and find out if they advance or clarify our understanding of how and when planets form and how their atmospheres evolve. The paper on this discovery was published in the Astronomical Journal. Joining us now is lead author Dr. Elizabeth Newton, an assistant professor at Dartmouth College who studies stellar astrophysics and exoplanets. Welcome, Dr. Newton. Thank you for joining us here today. So first off, did I summarize the paper properly? Is there anything you want to add or correct?
Mostly, yeah. In terms of the planet discovery, that sounded great. The one thing that I might adjust is that normally a stellar stream is exactly what you said. We're thinking about these streams in the outer Milky Way that are these accreted galaxies. In this case, the stream is more likely, we think it formed from a cluster of stars that was born in the galaxy. So not a dense cluster like the Pleiades, but a more kind of tenuous association that's, since it's been rotating through the galaxy for 100 million years, has been stretched out a bit.
Okay, well, thank you for that. So this system, TOI 451, why is this system interesting to you? What got your attention most about it?
Yeah, so the collaboration that I'm a part of, which is, as you said, the Test Hunt for Young and Maturing Exoplanets, or TIME, we're really interested in trying to understand planet evolution. And one way that we can do that is by finding planets at many different ages. So each of them represents like a snapshot at a certain age. And then we like take our snapshot from like 5 years old, or snapshot from like 10 years old. So like middle school and like kindergarten. And then we say like, how did this planet grow up? How did this human grow up over that time? So thinking about the science, the real interest is in kind of understanding this process of planet formation. In terms of why I was specifically excited about this system is actually more about the data itself. So I really liked the way all of these different observatories and teams and all of their work kind of came together to enable the discovery of the system. So
sorry, she does this every show pretty much. So
yeah, I usually often get my own cat company, but I'm in the kitchen, which is a lot colder than many of the other places I might sit. So
I just am really curious about that acronym. Did you help come up with that?
Yeah, it was a process. My husband helped too, and then we had a Slack vote where we had all the different options. Astronomers, yeah,
we can't be trusted to name things. I know.
we can't. But
we talk about it a lot.
Yeah. It's not too. At least I felt that it wasn't so convoluted as to embarrass me in the future. So
no, we give out an award here called the Babies Award, and I don't necessarily think that yours qualifies for it. So
I don't know what the award is, but I think I'm glad.
Well, let's just say babies is an acronym in itself. Okay, so when looking for this system, and you said that, I know you guys used a lot of data from different telescope. So it wasn't just test data. There was confirmation data that had to be taken from Spitzer, from ground-based telescopes. What was the process of confirming this system?
Yeah, so when we first found the system, which was shortly after the stream had been determined to be young, we started all this process of trying to get this new data. So this involved, many of these were programs that we already had in place because we knew we were going to be finding planets in the year 2019. So for example, I had led a proposal to Spitzer and said, we don't know what the planets are yet, but we know that we're going to find some, and we'd like to follow them up with Spitzer when we do find them. And so once we actually found the planets, then we went back to Spitzer and said, like, we want to use some of this time that you gave us now that we actually know that this planet is here. And so we had a couple different programs that were like that, where we were able to trigger observations, the target of opportunity programs. Once we had the target, we were able to trigger those programs. So that was many of the observations. And then we also worked with the test follow-up program to try to especially get ground-based confirmation of the planet transits. And that was a team of both professional and amateur astronomers all over the world. I
was going to say, is that the citizen science portion of the program, right?
Yeah. So there are many observers with their own observatories, and I imagine some of those might actually be listening now. And it is just amazing to be able to get to work with them and have the opportunity to get that data, which, we don't have telescopes everywhere. We don't have access to telescopes everywhere. And so it's a really great opportunity.
I think I talked about it with a couple of your colleagues last week, so we'll make sure to include that in the show notes, because that's a great program, and we do a lot of citizen science here at CosmoQuest. So really excited to kind of get some more people participating in that. What's unusual about these planets? What's got your attention on these three?
Yeah, the main thing is that they are so young. We don't know of very many young planets at this point. For the most part, these young clusters are far away, and the stars are too faint to first find planets, and then specifically also find planets that we can then hope to learn more about by studying their atmospheres with, say, the James Webb Space Telescope or with the Hubble Space Telescope. And so this system it's, you know, it's only about 125 parsecs away, or 400 light years away. And so it's relatively close in a galactic sense, especially for a star so young. And actually independent, so we got excited about the planet because it was young. And actually there was another group led by Ian Crossfield that independently identified it as a really good target for atmospheric studies. And so it happens to both be young and be one of these great targets for follow-up. And so that's gonna hopefully allow us to learn a lot more about what the atmospheres of planets or the compositions of planets are at young ages. And then because there's 3 planets, we can do this not just for one planet, but for 3 of them that are, you know, all formed in the, you know, the same protoplanetary disk. So it enables this, what we call a comparative exoplanetology.
Okay, that's really fascinating. I love exoplanets. We're going to take a short break, one last one, and then we'll be back with Dr. Newton. Welcome back. Once again, we are joined by Dr. Elizabeth Newton, lead author on a recent paper about the discovery of a 3-planet system around TESS object of interest 451. So, Dr. Newton, we were talking about exoplanetary atmospheres before the break, and I just want to get your take on what you think the James Webb Telescope is going to do for us when it finally launches.
Yeah, I think it's just going to be really surprising. So we had been talking before we started recording about what an amazing revolution data from ALMA was, where we just started seeing things in this detail that was just like completely unprecedented. And I think we'll be seeing the same thing with James Webb. We're just going to start seeing things, and we aren't going to know, you know, we have these expectations for what might happen under this theory or this one. And maybe that'll be like spectacularly confirmed with the first James Webb observations, which would be awesome. But equally as awesome would be us finding out that none of our observations exactly fit what the data are telling us, and we have to keep thinking.
I talk a lot on the show about how our planetary formation theories seem to shift and change with every new story that comes out, sometimes conflicting with each other. Do you think that we will ever really have a unifying theory of planetary formation, or are there just too many variables involved to kind of nail that down?
Oh, that's a good question. I might need to be more of a philosopher to give you the best possible answer for that. But I would say yes, we've come a long way in, really the past 20 to 30 years in terms of understanding planet formation. The main thing that we've learned is that it's so much more complicated than the picture that is painted in like an introductory astronomy textbook. And so I think it is going to take a long time to understand all of these different pieces. But as we get more data and as we develop more theories, I think that's something that is within reach. But it may, in the end, it may not be deterministic. There may be some chance that comes in to make a planetary system like the Sun versus a planetary system like TOI 451.
Right, and it's interesting to me because, of course, we start with this one example of a planetary system, which is our own, and then when we start looking for planets. I mean, obviously there's some observational bias because we're primarily relying on the transit method for the discovery portion of it. So we're seeing a lot of bigger planets around stars. So it's really interesting that, we find all of these different systems and basically almost none of them look like our own.
Yeah, it is. We are very biased, especially with the transit method especially with TESS, where most of these stars are only observed for 27 days. So we basically have, no chance at all to see something that would look like our solar system. Not to mention, just the geometric probability of a transit going down with orbital distance. But, I look at that and just think how amazing it is that there's all these things that don't look like our solar system out there.
Exactly. And that don't look like our Earth. So, finding all of these super Earths and mini Neptunes, that is so exciting. Would you count any of these in that category? I know they're 2 to 4 times larger than Earth. Would you say these are super Earths, or are we in the mini Neptune range?
That's a good question. I think there's some debate over, exactly where that distinction should be and whether it should be based on composition. I would say these are most likely to, with these sizes, they're based on previous research, most likely to have gaseous atmospheres. And so then I would probably call them mini Neptunes.
So the
or
closest
actual
one is
Neptune, I guess.
Or actual true, 4 times large. Okay.
Yeah.
So the innermost one is 1.9 times the size of Earth, right? And I know that I was talking about this last week with someone. There's a 1.8 gap in the size for that super Earth mini Neptune range. So this one comes really close. How accurate are these results? Are we certain that's 1.9? It just I really want to find a 1.8. I'm dying.
Yeah. So yeah, the transit parameters are measured pretty well
Okay.
for these systems. I think I can tell you what the error on the radius is. It is it's about 0.1, so it could be 1.8. It could also be 2 Earth radii. But the other interesting thing is that the location of that gap appears to depend on orbital radius. And so this planet is so close in that the gap may actually be at a different location than that kind of canonical 1.8 Earth radii.
Interesting.
Yeah, but there aren't very many planets at these really short orbital periods, so there's just not a ton of data to tell us exactly what's happening there.
So relative to our own solar system, how close are these 3 planets in orbit?
Oh, they're so close. So the orbital periods are, 1.8 days is the year on the innermost planet. And then the outermost one, so our coldest planet, is 16 days. So they're just vastly closer to their sun than any of the planets in our solar system.
So all within the orbit of Mercury.
Absolutely, all very much within the orbit of Mercury.
Wow.
Yeah. And since this, I would say this star is also very similar to the sun in terms of the luminosity and the mass. So right. we really are thinking of something that is equivalent to our solar system when we think about the distances.
So, okay. Wow. All right. So one last question. Do we think that since this is young, is there an expectation that if we could look at the system in say a few million years, we might be able to see like these planets have moved farther out, or are they pretty much in a stable orbit and they're going to stay where they're at?
Yeah, so based on what we currently know about the system, we would expect them to basically just stay where they are. And that's maybe not too surprising because we have found plenty of older systems that have similar configurations. So similarly, compact small planets on short orbital periods. So it has analogs amongst older systems. But there could be things that we don't know. Like if there's an outer planet, it could perturb the orbits of the inner planets. We can't currently rule out all of that parameter space.
Okay, well, thank you so much for joining us here today. What's next for you?
So we're working on a couple more young planet discoveries that we're really excited about. So one we might be able to measure a mass for, and another one I'm really excited about because it's in a young association that we don't know very much about, and I'm excited to learn about the association as we work towards understanding the planet.
Fabulous. Well, when you have those results, we'll have you back. All right. Thank you, everybody. This has been the Daily Space. You can find more information on all of our stories at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX. We'll see you tomorrow for Rocket Roundup with host Annie Wilson. Stay safe, everyone.